This is lecture 6, part C. Essentially what we're going to do in this one is introduce experiment 3. And so experiment 2, certainly not as long as experiment 1. Shouldn't be a big deal. Let's just toss a couple circuits down. This is going to be another short experiment, a similar experiment in that you're just simulating. You don't have to synthesize this in any way. So let's look at this, and this is a matter of implementing the ALU. Now the ALU stands for arithmetic logic unit. Generally speaking, in real life, it used to do arithmetic and logic. Technically, it just does all the stuff it needs to do. ALU is kind of a antiquated description. People don't really use that exclusively for arithmetic and logic, but they still call it an ALU. So here is our ALU. Typically, it's drawn like this A shape. Maybe that looks like for ALU, but the important thing is it takes in two operands, which I've listed as OP1, OP2. It does something to them, and it kicks out a result. So what you're looking at in this circuit here, it takes two 32-bit operands. It does something to them. I always call it bit crunching, and kicks out a 32-bit result. Now this ALU is required to do quite a few different things. Well, actually 10 or 11. I can't remember how many are on this list here. But these are the operations it's required to do. Now, most of these operations are very straightforward. Have you seen them before? Well, add and subtract, blah, 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 or and XORs, logic. These are shifts. The set if less than, they're kind of somewhat special instructions. Certainly consult the lab manual, the assembly language manual about those. Not a big deal. And lastly here, we got essentially this LUI, which is essentially a copy, and you'll see that in the manual also. So if you have questions about these instructions, exactly what you look at the assembly language manual. And so let's look more about this thing. So this is a kind of an expanded view of this thing. And what we have here, you're not responsible for these muxes in this experiment, but the idea of the ALU is it's going to get those operands, the two input operands, from a bunch of different sources. And certainly we have to select which sources we get it from, which we're going to do with a mux. So there's going to be a state machine in there that's controlling which of these sources is fed to the ALU based on which instruction is being executed. So this is, once again, you're only responsible for this ALU box here, but in later experiments you'll be adding other stuff to it. So the ALU, once again, is simulate only. There's a test bench file on Polylearn. You should use that. And also inside the experiment write-up, there is the expected outputs from the test bench. So if you get those outputs, you know that you did it right. Now, the issue is you have to put them in the right form. Now, with the simulator, I forgot what form I put it in. I think I have it in like a decimal output. So you make sure you switched your output of that ALU to decimal to compare the numbers. And so then the notion here, like I said, some of these operations are very easy. Just plop it down there. You've done it before, but some of them are not that easy, and you're going to have to consult the assembler manual, and certainly the RISC-V schematic also is going to help. But once again, you're going to run into the issue of signed and unsigned operations. So the idea here, I'm showing you an example of a comparison that's using, essentially it's casting some of these inputs to signed or unsigned. Now here is, this is like an equality operator. If A is less than B, blah, blah, blah. Well, the implication there is that it's interpreting A and B as unsigned numbers. Now the difference here is some of these operations I need to do signed operations, and what I'm going to do is use this casting to take my number and tell the synthesizer or whatever is interpreting that to interpret A as a signed number or B as a signed number. So once again, you're going to have to look through, you're going to have to understand this. There's some documentation out there. And more importantly, I'm going to tell you right now, there's some shift operations, like the typically arithmetic shift. You have to delve into the guts of Verilog or System Verilog, whatever you're using to do this, to figure that out. Now, it's to me, I never really liked using shift operations or shift operators. I always implemented them directly, but you don't really need to do that. You can actually use the shift operators, but you got to know how to use them. So there are shift operators in VHD or in Verilog, but you have to use them right. So by all means, for something like this, you might want to do a search on Verilog and arithmetic shift. It will tell you some really interesting information. And so this is the ALU as you need to implement it right here. These are the two muxes sitting in front of it. This is, once again, an old diagram, but up to this point, this was, we're getting there, okay? So this was experiment 1. This is given to you. That's going to be given to you. This is experiment 3. This is experiment 2, actually. This is going to be experiment 4, and this is going to be experiment 5. So we're getting there. We're not that far away from it. Just hang in there. This isn't too long of an experiment. This can fit very easily on one page. It's essentially an always block with a case statement in it. And the cases, of course, are going to be this ALU function select. Okay.